This part's pretty fun. I hope you think so. We're going to actually do some equations for kinematics in 2 dimensions. And you say we've already seen some equations, and I say, well, we get to see some more. These equations for motion with constant acceleration are very, very powerful. And I hope to ruin you. I hope that knowing these equations, knowing about the velocity, the acceleration, the displacement, that you're forever going to be looking at the world in a different way. You'll see a car going around a turn, you'll see the acceleration pointing toward the center. You see a car slowing down, moving in this direction, slowing down, and you'll say, oh, the acceleration is going in a minus, the acceleration vector is opposite the velocity vector. You see a car accelerating, you say, oh, the acceleration vector is in the direction of the velocity vector. I hope to ruin you. All right. And you say, you've ruined me already looking at that slide. That looks terrible. I'm not going to require you to do this derivation, but I want to show it to you once quickly so you know where these equations come from. We're going to derive the kinematic equations for constant acceleration. So the velocity is not constant, the position is not constant, but the acceleration is a constant vector. It's always a constant. Why is this an important case? And the answer is that if the force, as we'll see in Chapter 4, if the force is constant and the mass is constant, then the acceleration will be constant. So if you exert a constant force on something, then its acceleration will be constant. Very important case. Doesn't cover everything, but it covers a lot. Well, what is the average acceleration in the first place? It has a bar over it, so it means average. It's the change in the velocity divided by the change in time. Instead of writing that as a delta V, I've just written it as V, the final, minus the initial. Instead of writing this as delta T, I've written it as T minus T initial. No big deal. If we say that the average acceleration is equal to the instantaneous acceleration, as it will be if the acceleration is constant, and if we set t naught equal to 0. This is a special case also. This is the case in which you're starting your stopwatch at the initial event. The initial event happens when you start your stopwatch from 0. So I'm going to plug A into here, and we have V minus V naught over T, but we're going to set T naught equal to 0. So now, subtracting 0 just leaves a T here. I can multiply both sides by T, add V naught to both sides, and get V as V naught plus AT. That's this equation. That's the first of 2 kinematic equations for constant acceleration. Why is it useful? Well, it tells you that if you know the initial velocity and you know the acceleration, which is constant, and you know the time, then you know the final velocity. It's right there. It comes right out of that equation. And you'll solve a bunch of problems like this. There's one more equation. It's this one. These are the only 2 equations, and these you will commit to memory. We'll show them on the next slide. The derivation you don't need to know. Here's the average velocity. The average velocity is the average of the initial and final velocities. Well, to find an average, you add the 2 up and divide by 2. That's what this equation is. And if we substitute that into here, and we again take T naught equal to 0, then we'll get V. So I'm plugging this beast here into there. V plus V naught over 2, that's the left side, equals R minus R naught divided by T minus T naught, but T naught is 0. So it's just T. So, and then we're going to insert equation 1 for V. This equation here goes right into there. And let's see if we can do the algebra in our heads. We're going to multiply by t here. So we'll get v times t, but that's v naught times t plus a times t divided by 2 squared. So that's that last term that we talked about. Here's the v naught times t, and then we also have to add r naught to both sides. So that gives us an equation, r equals r naught plus v naught t plus 1/2 at squared. That's the derivation. That was quick. If you didn't follow every detail, it's all right. Here are those two same equations. This is all you need to know to be able to do kinematics in 2 dimensions. And there's a lot of power in these equations. They're vector equations. Write the kinematic equations for constant acceleration in vector and component forms. And define the variables that appear in the 4 component equations. So we're going to rewrite this equation in its components. Well, what's the x component of the velocity? Well, vx. There it is. What's the x component of initial velocity? V naught. V naught x. It's the initial component of velocity in the x direction. And those are down here. V naught x and V naught y are the initial velocities at time t equals 0. What's the x component of a? Ax. Well, t is just a scalar, so it comes along for the ride. So those are the 2 components for the for the velocity equation. Here are the 2 component equations for the position equation r. What's the x component of the position vector r? It's just x. Not rx, but just x, because the position vector is a very special vector. So this x component is x. X component of r naught is x naught. It's the initial position x naught, plus v naught xt, etc., like that. So these are the equations that you'll actually use in practice, but they both come out of here. And here are the definitions of all of the bits and pieces. The accelerations ax and ay are assumed to be constant. We assumed that in the derivation. These are the 2 final velocities at time t. The initial velocities are at time t equals 0, or t naught equals 0. Either way, that's when you start your stopwatch at 0. You 0 out your stopwatch, and the initial and final positions. All right. State the steps for solving kinematics problems. I recommend that you, if not these steps, you develop steps of your own to, sorry for walking off camera, to develop a strategy for solving these problems. This strategy works very well for me, and so I recommend it to you. So the first step is to make a drawing, including a coordinate system. So you get to choose. It's a free country. You can put x this way and y this way. In some cases, when we have blocks sliding down inclined planes, we'll have x pointing up along the plane and y perpendicular to the plane. You can put x up and y to the side. It's totally a free country. You choose the coordinate system. Define the initial event and the final event. So the initial event is when the time starts at 0. The final event is when the time is measured as t, whatever that value is. Sometimes you'll know the final time, other times you won't in these problems. Label these events. So you've got to figure out what the events are. What's my initial event, and what's my final event? Once you know what those are, then you label them on your diagram, your drawing. Write down the numerical values of all known variables. And look at the component kinematic equations. Those are the ones x equals x naught plus v naught xt, blah, blah, blah. And the vx equals v naught x plus ax times t, etc. And see which one of those you can solve. So the strategy here is you got, for 2-dimensional problems, you've got those 4 equations. One for vx, one for vy, one for x, and one for y. And that's a lot of equations to deal with. But oftentimes, you'll look at all those equations and you'll say, well, I can solve this particular equation for one of the variables. then you go ahead and solve for that variable. Once you find that variable from that equation, you can plug that into another equation to find the other variables. And step by step, you can find whatever it is that you need. Don't worry too much about whether the variable that you can find is the one that you need. Just solve for a variable that you're able to find and then back substitute into the other equations. In some cases, life is not simple and life is not nice. You have to solve two equations simultaneously for two unknown variables. You might have an equation that involves both x and y in it, and you can't find either x or y, but you have one equation that involves x and y, and another equation that involves x and y. In that case, you solve one of the equations for x, for example, substitute that result into the other equation, and solve that second equation for y, and then go back substitute to find x. Let's do an example. The displacement of speedboat. Speedboat has a constant acceleration of 2 meters per second squared. Happy day. It's moving in the x direction. So here's my x component of acceleration. I've chosen an x direction that's to the right. Now, what if I had chosen x to the left? Well, if I had said my positive x direction is to the left, but my acceleration is to the right, then I would have put a minus sign in here for the acceleration because it points in the negative x direction. But I make my life a little simpler by saying, let's have the x being in the direction of the acceleration. X is also the direction of the velocity. And so in that case, this velocity is positive, 6 meters per second. And its initial position is at the origin. So this is the origin of coordinates. Find the boat's position and velocity after 8 seconds. Well, let's do it. We need the position. Let's plug the values into this equation to see if we can find that final position. The steps for solving these problems are these 1, 2, 3, 4 steps. I remember them as D, E, V, S. I don't know what that spells, but I just think of it as devs. All right, D, diagram. We've got it. We've chosen an x and a y axis. And I got a diagram. E, for events. Let's label our initial and our final events. Well, this is my initial event. When I know the velocity is, my initial event is when the velocity is 6 meters per second. My final event is the event I'm interested in. I want to know what the velocity is at this final time. And we do know that this is 8 seconds after the initial event. So DEV, variables. So in this, we write down numerical values of the known variables. We've actually got them written down. V naught x is 6 meters per second. AX is 2 meters per second squared. T is 8 seconds. T naught is 0 seconds. So let's start plugging these values in. X naught, we haven't written down. That's the initial value of x. Here's the initial position. Here's the x-axis. The tip of the speedboat is at the origin at that initial time. What's its x value? 0. Because it's at the origin. So we're going to put in 0 meters for x, 6 meters per second for v naught x. T is 8 seconds. 1/2, this 1/2 that comes along for the ride. 2 meters per second squared, that's this acceleration. And then finally, time squared. It's not time square, but time squared. 8 seconds squared. So 8 times 8 is 64. 2 over 2 is just 1. And this is another example of carrying the units along in your calculation. Let's see if the units work out. Had we forgotten, for example, if we forgotten to square this, we would have gotten the wrong answer. And the unit analysis would have revealed that to us. Because when you square 8 seconds, that's 8 squared times seconds squared. That's 64 seconds squared. Well, the seconds squared cancel these seconds squared in the denominator, and the seconds cancel, and we get meters out of the deal, which is the units that we want to find. So I always put in the units, I really do, and I recommend the same to you. I'm a theorist. I've done thousands of pages of algebra, I think, on various calculations, and I still carry the units along just because it's good practice. It saves you from mistakes. All right, here do the units work out. Meters per second times seconds. This second kills that second. One in the numerator, the other in the denominator, and we get meters. 6 times 8 is 48. I get 64. 64 plus 48, 110 meters. So that's the position. That's how far it's gone after 8 seconds. What about here for the velocity, the final velocity? Well, we can use the velocity equation. Vx is v naught x plus ax times t. V naught x is 6 meters per second. Ax is 2 meters per second squared. T is 8 seconds. Plug the numbers in, you get 22 meters per second. So we've increased from 6 meters per second to 22 meters per second. And that makes sense. We're accelerating in the x direction. That second final velocity should have been larger than the initial one. Catapulting a jet, another example. Jet is catapulted from rest in the deck, reaches a final speed of 60 meters per second. In this case, we know the final speed, and we know the initial speed is 0. And we're asking about the distance that it travels during this process. And you better have this calculation right, because if it's not up to flying speed by the time it reaches the end of that deck, you're going to have an aircraft in the ocean. So we're actually looking for the distance that it travels. We want x. The trouble with x is that we don't have enough to find x. We really need the time. So rather than get discouraged, we simply try and find an equation that we can solve for something. And in this case, we can solve the velocity equation for the time. This is the final velocity. This is the initial velocity. This is the acceleration that we know that the ship experiences, 40 meters per second squared. Well, you can solve that equation for time, no problem. This is just 0. Divide by 40 meters per second squared, 60 meters per second divided by 40 meters per second squared is 1.5 seconds. How do you know that? The meters cancel. One of these seconds cancels one of these seconds, and we're left with 1 over 1 over second. 1 second left over. And 1 over 1 over second is just seconds. So there's 1.5 seconds. That's how long it takes. That's how long it's being accelerated up to this final time. So the final time is 1.5 seconds. And now we can find the distance because we've found the time. Time goes in here, 1.5 seconds. Just plug in the numbers that we already know. V naught x is 0, x naught is 0, and we find that it goes 45 meters. Deceleration versus negative acceleration. A car traveling along a straight road, decelerating. Which one of the following statements correctly describes the car's x component of acceleration? If x is in this direction, Well, it kind of depends. Because if it's traveling, in this case, it's traveling in the plus x direction, and it's decelerating, it's slowing down. That means this velocity is going to get less and less and less. That says that the acceleration has to be in the negative x direction. Positive x this way, negative x that way. But there's another way that this can happen. If the car is moving in the negative x direction. So here's the positive x direction. The positive x direction is to the right. The negative x direction is to the left. If it's slowing down, then the acceleration has to be opposite the velocity. And therefore, it can be either negative or positive. The acceleration vector must be opposite to the velocity vector. But the velocity vector could be either in the plus or the minus x direction. Another quick example, lots of examples. Spacecraft is traveling with a velocity of 3,250 meters per second. That's pretty fast. The retro rockets are fired, and the spacecraft begins to slow down. So it's moving this way, begins to slow down, and its acceleration is 10 meters per second squared. And that's the magnitude of the acceleration. What's its velocity when the displacement of the craft is 250 kilometers relative to the point where the retro rockets began firing? All right, it's a free country. We can choose the direction of the x-axis. Let's take x positive in the direction of motion, this initial motion. And we're asking about the velocity when the displacement is 215 kilometers relative to the point where the retro rockets began firing. Let's work it out. Here's the x component equation, x equation. It's 215 kilometers, the final position. Initial position we take to be 0, initial velocity, time. The acceleration we take to be negative 10 meters per second squared. Why not 10? Why did we take the acceleration vector to be negative 10 meters per second squared? And you say, because the acceleration vector is opposite the velocity vector. Here's the velocity, here's the acceleration. It's slowing down. So the acceleration vector must be opposite to the velocity vector. If it were speeding up, the acceleration and the velocity vectors would be in the same direction. So we've got to take that to be the, and we've taken the x direction to be positive in this direction. The acceleration vector is therefore in the negative x direction. So plugging in minus 10 meters per second squared for this acceleration, then we have a quadratic equation. If we drop the units just for this purpose, just for these two steps here, and try and solve for the time, t, then we've got a quadratic equation to solve. 10 divided by 2 is 5, so that's this term here. And I've taken it over to the left-hand side of the equation. So taking it to the left side of the equation, I turn this negative into a positive when I add it to both sides of the equation. This term I also take to the negative, to the left side of the equation. It's a positive term. It becomes negative when I take it over to the left side. And then this 215,000 comes along for the ride. Well, The quadratic formula comes into account here. Ax squared plus bx plus c equals 0. X is minus b plus or minus the square root of b squared minus 4ac all over 2a. Plug these numbers in to the quadratic equation, or the quadratic formula. If that's a little hazy in your brain, you might want to review it. Ax squared plus bx plus c equals 0. The solution to that is x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. And you should, that would be one mathematical fact that I would expect you to bring from your previous education, or to just brush up on it a little bit if it's a little bit hazy. Plugging these numbers, a, b, and c, into this equation gives not x, but t. And we get two different values of t because of this plus or minus here. And so that says that there are two different times when the spacecraft hits the 215,000 meter mark, or the 215 kilometer mark. That's kind of embarrassing, isn't it? And I say, no, it's illuminating. It's awesome. Let's see what these two values are. 325 plus 250 would be 575. 2 plus 3 is 5. 5 plus 2 is 7. And then the other possible time is 325 minus 250. Well, the difference between those is just 75 seconds. What do these two times mean? And how come you're getting two times? Is there some kind of mistake? The answer is there's physics in this. After 75 seconds, the spacecraft gets to this 215 kilometer point. But it's still slowing down. So it slows down. So here it's going 3,000 meters per second. Here's it's going 2,500 meters per second. Here it's going 0 meters per second, but it's still slowing down. Its acceleration is still in this direction. Now it starts to speed up. And it again crosses this 215 kilometer point, and that's at that later time of 575 seconds. So you don't have to guess. The math tells you that it's going to be at that 215 kilometer point at two different times. All right, and then if we want to find the velocity, we just plug in the final velocity be the initial velocity, the minus 10, the time t. We can plug in these two different values of the time t, 575 and 75, and we get that the speed is 2,500 meters per second, plus or minus. So in this case, the spacecraft starts here, slowing down, reaches the 215 kilometer mark, and it's going 2,500 meters per second. Slows down some more, turns around, comes back here. Now when it's back to this point, it's going negative 2,500 meters per second. It's going in the opposite direction. So the bottom line here is that sometimes the kinematic equations give two answers, each corresponding to a different event. In this case, this is the first event when it first crosses this point, and this is the second event when it second crosses that event, it crosses that point, moving in the opposite direction. One more example. Motorcycle ride consists of two segments. During the first, the motorcycle starts from rest, has an acceleration of 2.6 meters per second squared. So he's going to accelerate. Let's take this to be the x direction. has a displacement of 120 meters. During the second segment, the motorcycle slows down with an acceleration of 1.5 meters per second squared. Until its velocity is 12 meters per second. What is the displacement of the motorcycle during the second segment? All right, it's a challenging problem. Let's write down what we know for the, what else do we know? We know that he's starting from rest, so V0x equals 0. We don't know what this value of velocity is, but we do know what the value of velocity is here. It's 12 meters per second. So this is going to be a variable. And so during segment 1, we can write the x equation and the velocity equation. X equals x naught plus v naught x t plus 1/2 ax t squared. And the final x is 120 meters. Here's x equals 0. Here's x equals 120 meters. So this is final. X naught is 0 plus v naught x. Well, that's 0. He's starting from rest. That's the initial velocity in the x direction. Times time. That's the final time here. Plus 1/2 ax is 2.6 meters per second squared times t squared. Well, we're really looking for the displacement of the motorcycle during the second segment. Well, we're not going to have any hope of finding that displacement of the motorcycle during the second segment. We know the first displacement of the motorcycle during the first segment is 120 meters. But we're not going to have any hope of knowing how far he's going during the second segment unless we know how fast he started in the second segment. So this segment 1 gives us the key to this understanding. I can now solve this equation for t. This is just 0. This is 0 times t, which is 0. And I can multiply both sides of this equation by 2. And then divide by 2.6. So, well, actually, the easier way is just to say 2.6 divided by 2 is 1.3. And then divide both sides by 1.3. So that gives me 120 meters divided by 1.3 meters per second squared. That's just a straight line through here, equals t squared. And to find t, I can just take the square root of both sides. Check the units. The meters cancel. We have 1 over second squared. That's the same as having the second squared up in the numerator. And we take the square root of second squared, and that's just seconds. And this gives some number of seconds. What's it going to be? 120 divided by 1.3. That's about going to be 100. If this were 1.2, it would be exactly 100. Divided by, or the square root of 100 would be about 10. Plug that into your calculator just to see. So we say that it takes 10 seconds for him to get to this point here. Knowing this time now, we can find his velocity here. Let's find his velocity. Vx is v naught x, and we're looking for this velocity right there at that midpoint, plus ax times t. Well, we don't know this velocity. That's what we're looking for. V naught x, the initial velocity, is 0. That's this initial velocity for segment 1, plus the acceleration during segment 1, which is 2.6 meters per second squared. And now we know the time. It's about 10 seconds, and you can plug in. So this is going to be only approximate. So that's going to be something around 26 meter per second. Now you know what the initial velocity is here. And I'll let you, as an exercise for you, well, I'll just sketch it out here. Now we know his initial velocity, his final velocity, and we want to find the distance traveled during that second segment. So this is segment 1. Now we're talking about segment 2. And so the key here, you're going to attack this problem in the following way. Vx final equals Vx initial plus Ax times time. So what you'll do is to plug in the final velocity of segment 2 is 12 meters per second. The initial velocity for segment 2 is the final velocity for segment 1. So as he's accelerating in segment 1, he reaches some intermediate velocity, then he starts slowing down. And so this is going to be about 26. The acceleration during segment 2 is negative 1.5 meter per second squared times t. So what you'll do to finish this problem, we're out of space, you can solve this equation for t. Once you find a value for t, and it won't be negative because when you subtract 26 from both sides, 12 minus 26 is a negative 14. And then you'll divide both sides by negative 1.5, and a negative divided by a negative is a positive. So you get a time out of that, and then if you want to find the distance during segment 2, then you'll appeal to x equals x naught plus v naught x t plus 1/2 ax t squared. Now you'll have everything that you need. You've got t, you just solved this for t. You've got ax, it's negative 1.5. You've got v naught x, it's this 26 meters per second. You've got x naught, and you can take that to be 120 meters, and that will give you the final distance x. And then I subtract x naught from x to find how far he went. You subtract 120 meters from your final result to find out how far he went during segment 2. That's how to set that problem up. Motion in one direction. In the x direction, looks like this. You've got the two equations, the velocity equation and the x equation, if he's only moving in the x direction. Well, motion in the y direction, if he's only moving in the y direction, then you've got two equations involving y. What happens if he's moving in both? And the answer is, you can treat each component separately. You've got these two equations to deal with in the x direction, these two equations to deal with in the y direction, and this allows you to have at it in 2 dimensions. All right, let's do a quick example. A moving spacecraft. In the x direction, the spacecraft has an initial velocity component of 22 meters per second and an acceleration of 24 meters per second squared. In the y direction, the analogous quantities are blah, 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 and blah, blah, blah. At time 7 seconds, find x and vx, y and vy, and the final speed of the spacecraft. Nice thing about this problem is there's only one segment. So we're only talking about one particular acceleration. So let's talk about x. We've got x equals x naught plus v naught x t plus 1/2 ax t squared. Let's find how far he goes in the x direction. That's one thing we want to find. X naught, let's say that's 0. We can oftentimes take that to be 0. V naught x, we're actually given initial velocity of 22 meters per second times time at a time of 7 seconds, it says here, plus 1/2, and the acceleration is 24 meters per second squared times 7 seconds, quantity squared. We can plug all those numbers in and get a number for x. It'll be some number of meters. Vx, v naught x, plus ax times time. We're going to do the same thing. We got v naught is 22 meters per second. Acceleration is 24 meters per second squared times the time, which is 7 seconds. That will give me Vx. Then we're going to do the same thing in the y directions. Y equals y naught plus v naught y t plus 1/2 ay t squared. Plug the numbers in. I'm running out of space here. Let me write this a little bit bigger. Y equals y naught. Well, why not? Plus v naught y in the y direction. 14 meters per second is the initial component of velocity times 7 seconds plus 1/2 times the acceleration in the y direction is 12 meters per second squared times 7 seconds quantity squared. Plug the numbers in and you get some number of meters. And then similarly, Vy is v naught y plus ay times t. V naught y is 14 meters per second. That says 12 if you can't read it. Times 7 seconds. Plug the numbers in. That'll solve that example number 1.